There is this another method called eye tracking. This is a very famous painting of someone who I don't know. Anyone knows whose painting is this? Okay, so I'm not sure. This painting actually has lots of people, and when you do an eye tracking on this, eye tracking basically is that where are you looking at this picture? This was first done in 1967 by a person called Yarbus. He did this eye movement, and he did not have that eye tracking device, but these days we have eye tracking devices. You can actually go and buy, and these days actually they have interactive eye movement devices also. But anyways, there are 6. 1, 2, 3, 4, 5, 6, and the 7th one. The experiment was, come, and I am happy that you came, look at that image, and then just look at it first. So that was the brain eye movement. Since he did not have eye movement, he actually drew it by looking at the eye or some mechanism. Then the questions changed. The question was, one question, how rich they are in this picture. Rich, or how wealthy they are. How much money do they have? Okay, look at the image. You will find that how do you judge the affluence or money or wealth from a picture? You will look at their furniture, clothes and other things. The second question was, how are these visitors is a family member or unknown fellow? How will you decide that? You will look at the faces of people, not at the other things, furniture and other things you will not see. You will look at their faces, eye and other things. Then different questions were asked, and all of them produced different eye movements. So the point was that the information from an image is not obvious. Only when you are asked a particular question, you look for it. So it's an active information gathering. Same image, 100 people will see, but the motive changes. So intention tells you what to look for. So this was an eye movement. These days, Tobii is one of the eye tracker companies. They produce eye tracking. Okay. For sports, for shopping, you have no idea that how much research is happening on shopping. How do you actually shop? I'll show you a video. It's a small video again. 2 minutes video. These red dots are basically where you are looking at. So you are having a glasses of eye tracker. Now this is a gaze plot. Basically what it means is that how number of people have actually seen, and these the traditional way of analysis is that number tells you about saccades. Now I should tell you what saccade is. Saccade is your eye movement, so your pupil moves from one to another, like one direction to another direction. It takes time. If you move your eyes, you are actually not moving your head, but only the eye movement is the duration which is called saccade. And it is said that the average human eye saccade is around 250 milliseconds. So your eyes do not remain still. It keeps moving. And there are lots of other parts also, perception will talk about it, that when for 250 milliseconds you have a gap, you do not have information from that information, because your eye is looking at one point, then it moves. So there is a time taken, 250 milliseconds. Then you look at another object. This duration, they say that in a day, is around 20 to 25 minutes. So in a day, you have no idea 20 to 25 minutes where it has gone, because you do not have information from that. Because that's the time your eye moves. And that is called saccade. So these numbers basically represent that first you saw this and then you saw that, then there's a sequence. And these blown up is that how much time you have looked at it. If you are interested in particular object, you are looking at it for longer period. And then people actually now these days, I know one of my friends, he is working in a Indian company, it has big malls. And they do a lot of research actually that where to place your products. And it's again, if you go and you have a card and other things, there is a statistical method also. But in this case, people want to find out that if I go for a particular purpose, I buy milk, and then what I look for. Am I looking for bread or am I looking for something else? So arrangement of mall products is a big deal, and people do a lot of research on this. We'll talk about it later also. This is interesting. This particular experiment actually was done to give us an idea that how we develop. I'll talk about that experiment later, but this is an experiment. Okay, so I hope that you cannot see this bottle, right? You can see the bottle? You can see it now? Now? Where the bottle will come out? If it's still in moving direction, and I say that I'm moving it, where will you expect it? On my left, right? And then you see it. Hooray! What kind of experiment? Children, if you do it with small infants, you know why this happened? Because we have an idea of, or the concept that bottle suddenly does not disappear. When it is an object, it remains an object, and in a movement it will come from this side, even if it is blocked for a period of time. So there is a concept of continuation of object. We know that things continue. But children or infants do not have this concept. They have to learn it. So this eye movement experiment, I like it very much because it did the eye movement of very small child, 4 or 5 months, and see what exactly happens. Object representation, a 5-month-old infant. This is the gaze of that small child. If you do it with big people here, and then suddenly you should see your gaze here. But children lose it. The moment the object is behind the box, it's a long video again, but the point is that Children have to learn this thing. Things that are very simple, but again you see that how one method of experimentation tells us that how we learn. There is Mary Ann or Sally Ann story, you know, which talks about theory of mind. I'll talk about later. One more thing. Eye movement is not just the movement of eye. Actually, they say that eye is basically extended brain. There is a direct connection, and it, you know, this from this part it has to go to the other side of the brain. But your pupil also dilates. There was one experiment, very simple experiment. Okay, yeah. So the experiment basically was this. It's a very funny experiment, but what the experiment was, participants were shown images of women and faces, and they were asked to decide who is more beautiful. It's a very simple experiment. I can see an image and say, she is beautiful. But what they did was that they took half of the people who had their pupil dilated, and half of the women who did not have pupil dilated. And the experiment suggested that 99% of the time, dilated pupil women were considered more beautiful than women who were not having that pupil dilation. Now, pupil dilation is also connected with lots of emotional aspects. When you are happy, your pupil dilates. When you are sad, your pupil dilates. Pupil dilation basically means this. With light, you can check whether your pupil is dilating or not. So, size of that, it contracts and it expands. And that expansion and contraction is quite big. There is a newer experimental work which is going on. Even I have conducted an experiment on that. Is that cognitive load. When you are looking at this whole presentation, the entire class you are sitting through, your brain is doing a lot of work, taking information and then trying to make sense of the sound, the language, accent, a lot of things are happening. And that is called the cognitive load, that your brain is putting a lot of effort. And it seems that when you do a lot of cognitive effort, your pupil dilates. And you can actually measure that if particular stimulus or an object giving you enough of cognitive load or not. So in education, people do a lot of study where you ask a question and measure how much the cognitive load is put because of this question. Anyways, the last one is the method that is now very important for us to understand the brain. You notice that single cell recording we saw, single cell recording you can actually find out brain areas and neurons also, but you can't do it with human beings. It's very difficult. EEG or electroencephalogram we saw, it has problems because it does not tell you or give you the big picture. You don't know which part of the brain is activated. Behavioral experiments tell you the phenomena but does not tell you the reason. PET, or which is called positron emission tomography, or fMRI, functional magnetic resonance imaging, they are actually telling you what is happening in your brain when you are doing a task. Okay, so I'll show you a video. Functional magnetic resonance imaging is the latest one. It has a huge magnet and you are sent into that magnet. Anyone who has gone through MRI? No? You all are perfectly healthy? But MRI is a normal procedure. Again, patients go through it. I have been there once, but I slept. I don't know why, but somehow for 1 hour experiment I slept. My data will be useless. But it's a huge magnet and it keeps rotating. Every 2 seconds or 1 second, it matters. 2 seconds or 3 seconds, you have, depending on the size of your or quality of your fMRI machine, timing also changes. So it takes one picture of your brain every time it moves, and it takes the 3D image, and it can tell you that which part of your brain is activated by measuring the consumption of oxygen. So when your brain does something, it consumes oxygen, and then that is recorded, and that's where it happens. So let's get an idea of how fMRI works, and then I'll show you a language experiment. That will be the last one.
The most widely used method for finding out what parts of the brain we're employing when doing a task is called functional magnetic resonance imaging, or fMRI. Because the huge magnet you go into means anything metal would get sucked in too, filming close to a real machine is impossible. So to find out how fMRI works,
okay, Ellen, we're done. I can take you out now.
I tried out a fake scanner, courtesy of one of the world's experts in brain imaging, MIT's Nancy Canwisher.
That noise is
How
very
was that?
convincing. What is this? You use this to
This is called a mock scanner. We use this because we scan a lot of children, and we want them to be used to the scanning environment.
When your brain is being scanned, what's going on in this functional MRI?
Okay, so each beep you hear is a picture that we're taking of a slice through your brain. And what's special about functional MRI is that the brightness of each part of that image tells us how much neural activity is going on in that part of your brain.
Why the brightness? What does the brightness have to do with it?
The basic idea is that neurons are like muscles. So if a part of your brain turns on, say right here, and the neurons start firing there, it's just like using a muscle. You need to send more blood to supply those neurons because it's metabolically expensive, just like running with a muscle. And so what happens when more blood is sent to that part of the brain is that the amount of oxygenated hemoglobin in that part of the brain changes. And that has a magnetic signature that we pick up with functional MRI. Your brain is a three-dimensional object, and we take pictures of it by making a series of slices, for example, like this. So we might choose, if we want to cover your whole brain, a series of 20 horizontal slices like this. And then within each slice, we have a nice 2D picture of what's going on in that slice. Each bang that you hear during a scanning sequence is a little radio frequency.
Okay, so fMRI is a very interesting thing. If you ever get a chance, Big Bang Theory, have you seen? Some of you? And you saw that when Sheldon met Hofstadter's mother, and he went for his brain scanning, and he said that I love to see my brains. So you can actually see your brain in MRI, but it's expensive. But if you have insurance, make use of it. Go see if you actually have or not. Or at least you will have a record. Yes, I have a brain. And it's not dangerous. Just get inside it. There are people who, for experiments, they do it for money. Okay, so the last, based on PET, is one thing that is this video. This video actually is again a part of real experiment. It talks about language processing in brain. First video we saw was the insertion of dye and anesthesia, but that was an invasive method of checking your brain functioning. This is a non-invasive method of testing. It's a long video, and then we'll stop.
If language is somehow built into the brain, it should be possible to explore how it's processed. Today, we can actually watch the brain at work as it deals with the basic building blocks of language, words.
I think it's important to understand the process of language, which I think is inherently interesting in understanding how the brain works. It's one of the things that characterizes us as humans. And I think to understand that leads us a long ways to understanding how the brain works in a more general
Just
sense.
to add to this particular thing, they have two different conditions in the experiment. One is that the lady is asked to pronounce or produce verbs, and the other one is just nouns. But you see that when verb is produced, which part of the brain activates, and when noun, which part of the brain activates.
Are you comfortable in the chair the way you are now?
Pretty much.
Rakel's team uses a PET scanner to examine the brain areas involved with language. Harmless amounts of radioactive material are given intravenously to Patty Crippen, a volunteer. The brain areas that are activated when she uses words will absorb the radioactivity.
Patty, this will be fairly warm going on.
Okay.
The thing that had to be developed was an experiment that simplified the whole process.
This will help to hold your head still.
And in our particular case, we decided to look at the processing of a single word. But it wasn't just as simple as that either, because obviously you could say, well, we'll just present you a word and you either look at it or repeat it. But this brings into play many different parts of the brain as you process that. So it was not only simplifying the task, but learning how to break even that simple task up into its component parts.
Okay, now we're going to go ahead and put you in the machine.
When we do a PET study to look at language performance, we do this in stages.
How's that?
We begin by just a control scan where you're just looking at a blank screen and see nothing. We consider that kind of the step one.
Okay, Patty, we're about ready to start.
Okay.
Next, Patty reads words silently off the screen.
The word should start in just a second.
Okay.
Silently she is
When
reading
one
the word.
reads a word, one can envision a number of things being involved here. First off, you look at the word, and so you activate, very clearly, you activate areas of the brain processing the visual image of the word. When you look at a PET image, of course, you see it on a computer screen. And what you see then is this rather colorful image, which represents a horizontal slice of the brain. And it's as if you're looking down on the brain from the top, so that the nose is up around 12 o'clock and the two ears are to the side, and the left's your left and the right's your right.
Now, the image produced when Patty first looked at the blank screen is subtracted from the one produced when she read the words to herself. The result pinpoints areas that were active only when she was reading. The most active brain areas were processing visual information, specifically the words Patty saw.
Word, Patty?
Uh-huh.
Okay, that was very good. What we're going to do next is the simpler task where you just repeat the words out loud.
Okay.
Okay, open your eyes now and begin.
Bed, fan, reel, rifle, clock.
We've now taken it up a step in complexity. Now you're using the vocal apparatus, you're repeating the words, and you immediately activate areas of the brain that are concerned with the movement of the mouth and the movement of the tongue. So you get very hot areas on both sides, roughly in the middle of the hemispheres.
These are areas that operate Patty's vocal apparatus.
And that becomes the control for the final step, in which you're shown the...
Okay, so when you just read it without producing, just repeating it, when you read it or speak, your motor areas also get activated because now your muscles are activating. Your last condition is this.
word, and you're asked to produce another word.
Okay, Patty, if you open your eyes now, you'll see that words are going by on the screen, and they're all nouns. And what we want you to do is generate a verb that's appropriate to the noun or a use for the object. So if cake came up, we'd like you to say eat, or if gun came up, we'd like you to say shoot, something like that, all right?
Okay.
Okay, go, Patty.
Bake, fly, twirl, climb, heat, watch, listen, hit, swim, drink, drive, blow, ride, knit, ring, turn, sit, shoot.
So in all these conditions, there is a noun said, and you have to produce a verb associated with it. So TV, watch, gun, shoot. And when you do that, final thing is that your motor areas are highly activated when you are saying the verb. Anyways, again I'll upload this thing and you can watch. Next classes will have less of videos. So I can still tell you that, but they will be interesting because now we'll be talking more about higher stuff, conceptual part and theory part. This was a PET study, positron emission tomography.